This video is going to be covering section 6.1 stability and the phase plane. And before we get started, I'd like to talk about where we've been so far and then where we're going. Chapter 4 in our textbook was covering some very basic systems of equations in which we could solve them using substitution or elimination. In other words, we were working with a system of two equations, two unknowns, or two dependent variables, and we were able to solve for one of those dependent variables, plug it back into the remaining differential equation, and reduce it to a single higher order differential equation and solve from there. One of the other skills we also practiced in chapter 4 was taking a higher order differential equation and rewriting it as an equivalent first order system of differential equations. In chapter 5, which we just completed, we talked about solving linear systems of DEs via the eigenvalue method. In other words, we were able to use matrices in order to solve linear systems. You'll notice that chapter 6 is going to focus on nonlinear systems, and so we're going to see how we can still utilize matrices in the event that our systems are no longer linear. So again, in 6.1, we're going to talk about stability, which is something we've seen previously. We've talked about in the lower dimensional case what it means to be stable, semi-stable, and unstable. And we'll talk about the phase plane. So we have also drawn phase portraits. This is just an extension of what we learned previously, only in higher degree. So we have a reminder here in section 2.2, we talked about if we were working with autonomous first order differential equations. And remember what autonomous means is on the right-hand side, the independent variable t is not missing, or is missing rather. So only the dependent variable is showing up on the right-hand side. And we found what we called critical points by setting the function f of x equal to 0. This is no different than what we learned in Calc 1, where we set derivatives equal to 0 to find critical points. Here, the derivative already is f of x, so we're setting that derivative equal to 0. We check their stability by drawing a phase portrait. And so if you'll recall, we would plot our critical point, let's call it C, and then what we did is we looked at the sign of the derivative. And so let's say the sign of the derivative on the right was positive. We drew arrows pointing in the positive direction. And then as an example, if the derivative was negative to the left of C, we drew arrows in the negative direction. And then what that meant is that the solution curves were diverging away from C. So we would have then classified C as unstable. So that's just a reminder of what we worked on in section 2.2. This section is going to just generalize these concepts. Instead of looking at a single differential equation, now we're looking at systems. So you can see our first definition here is going to be working with the system. You'll notice that this also is omitting the independent variable t. So that's what I have listed here. They're independent of the time variable t. So this is called an autonomous system. Instead of an autonomous equation, now we have a system of two equations. And what we get is we can solve this system for solution curves, x of t and y of t, and that gives us a parameterized solution curve. So again, the parameterization just means that we have a definite orientation to our solution curves. Any such solution curve is called a trajectory of the system. So how are we going to find these critical points? Very similar to what we did in section 2.2, we want to set each of these equations, capital F and capital G, equal to 0 simultaneously. So they're equaling 0 at the exact same points, which is what I have denoted here by x sub star and y sub star. It's important that it zeroes out both functions at once. Once we find our critical points, then we consider these constant functions, x of t and y of t, to be equilibrium solutions. So a lot of times students say, what does that triple equals bar mean? It just means that I'm equivalently defining the function to be that constant. Not that I'm replacing that function with a constant, but it is the constant function everywhere. So I'll note that. All right, so we get our equilibrium solutions, and let's go ahead and look at our first example. We want to begin by finding the critical points here. So I'm just going to use the definition that says I need to set each of these functions equal to 0. So let me set that up first. And since they both need to equal 0 at the same time, you can solve this in whatever way you see fit. I'm going to work with the second equation since it's easier to find that, and then I'll plug it in to the first to solve for y. So this first equation gives me two different possibilities for x, namely plus and minus 2. So now I'm going to plug those in, but I have two cases. So first, if x equals positive 2, then what does my first equation become? It becomes 2 minus 8 minus 15y equals 0. So I have negative 6 equals 15y, or y equals negative 6/15. So this gives me, and actually let me simplify this. I can divide by 3, negative 2/5. So this gives me the critical point, 2, negative 2/5. So there's one of my critical points. And then the second case is if x equals negative 2, then 2 plus 8 minus 15y equals 0. So I get 10 equals 15y, or y equals 2/3. So my second critical point is negative 2, 2/3. All right, so again, just a system of two equations and two unknowns here. You'll notice that equation 2 was not linear, so you're not going to be able to solve this with matrices in your calculator, but these problems are fairly straightforward, so you should be able to solve them by hand without much trouble. All right, so we'd like to be able to visualize the solution curves of these systems. And so that brings us to a phase portrait or a phase plane picture, same thing. It's a picture that shows the critical points together with a collection of typical solution curves. So you should see these curves either emanating from or converging to your critical points, or perhaps flowing uniquely around them. So we'll see some different ways that these critical points are going to arise. But what I have here is a phase plot for the problem that we just worked on. And so I have here down below, recall we just found these two critical points, and you can see those lurking up here in our phase portrait. So the point 2, negative 2/5. So here's positive 2 on the x-axis, and negative 2/5 is this point here that I just highlighted in red. And then negative 2, 2/3. Here's negative 2, and here it is. So you'll see kind of this swirling action around the negative 2, 2/3. And then we have this saddle-like action happening at 2, negative 2/5. So I want to bring your attention to a tool that I want you guys to utilize for your homework, and that is how to draw these phase portraits with the computer algebra system. And so what I'm going to recommend is Wolfram Alpha. It's just a free website that's produced by the same makers that make Mathematica. So for those of you who are already in our lab course, Math 334, you should be very familiar with this notation, but for those of you who are not, you can see right below here, I have written the command that I used to plot this phase portrait. So the syntax or the built-in command that you're using is the stream plot command. Make sure you capitalize the S and the P in stream plot. And then you want to surround everything after the stream plot command in square brackets. And then you have three lists here. This first list is the two differential equations. So let me just scroll up here. All I did was I took the x prime and the y prime differential equation, and I put those together separated by a comma and encased in curly braces. These last two curly braces are just lists to tell Wolfram to output your plot from -5 to 5 in both the x and the y direction. So what I'm going to do is I'm going to pull this up so that you guys can see how to input this in Wolfram. So you can see right here, this is just wolframalpha.com. It's just a free website that you can use, and I'm going to enter in exactly that code from the notes. So stream plot, again, capital S, capital P, square bracket, and then curly braces and list your DEs. So 2 minus 4x minus 15y, comma after the first DE, 4 minus x squared, close your brackets, and then commas to separate your lists. So now I'm going to say output a plot for x from -5 to 5, and output the plot for y from -5 to 5. And then close off your square brackets, hit return, and you can see this beautiful output that it's going to give. So go ahead and have this web page up while you're working on your homework, because your homework will require you to sketch some of these phase plots. I will never ask you to do this on your own without the help of some kind of computer algebra system. So I encourage you to bookmark this page. All right. You can also visualize these fields by constructing a slope field, which we've seen that phrase before way back in chapter 1. And what we're going to do is take the quotient of the system. So we want to look at y prime over x prime. And so we get the ratio of these two functions. All right, so a critical point can be classified in several different ways. And so now we just want to classify what's happening in these autonomous systems, where the critical points are and what they look like. So for our first definition, we're going to talk about what's called a node. The formal definition is the following: either every trajectory x approaches your critical point x star, y star as t goes to infinity, or every trajectory recedes from that point. So there's two ways: either you're approaching it or receding from it. And important, right? We need both of these things to hold to classify a critical point as a node. Every trajectory is tangent to x star, y star, is tangent at x star, y star to some straight line through this critical point. So we're going to draw a couple of pictures that'll illustrate what these nodes must look like. But first, we can actually refine our definition of node further, and there are two different types of nodes. A node is called a proper node, or I like to think of star point, and you'll see why, provided that no two pairs of opposite trajectories are tangent to the same straight line. And it's called improper if all trajectories except for a single pair are tangent to a single straight line. So what I want to do right down below here in this white space is draw examples of a proper and an improper node. So let's do a proper node here on the left. And then we'll do an improper node on the right. And so just draw two sets of coordinate axes. All right, and so I had mentioned that proper nodes are often thought of as star points or star nodes because they look like stars. So what I'm going to assume is that in both cases, my critical point is at the origin. A proper node, remember the definition of the node is that the trajectories either need to approach or recede from that point. I'm just going to choose to have my trajectories approach it, so they're going to be going into that origin. And then proper says that no two pairs of opposite trajectories are tangent to the same line. So what I'm going to do is draw several examples of lines through this node, and these each are separated. Each straight line is actually two trajectories, so those are considered opposite trajectories. I'll draw one over here. Again, we're always going to be going either toward or away from our node. You can have your trajectories going along your coordinate axes, and you could draw in any other trajectories you wanted, so long as they're not tangent to any of the others. So for example, I could sneak one in here and so on and so forth. So this node at 0, 0 here would be considered a proper node. And so maybe I'll just highlight that node here in red. An improper node, the difference is that all trajectories except a single pair are tangent to a single straight line through the critical point. So in this one, I will also have all of my trajectories approaching my node. And let's just go ahead and let the x-axis be my straight line. But then I want all other pairs of trajectories to be tangent to that line. So for example, I could have these parabolic trajectories that are emanating in towards my node, and have a few more. We could have some in lower half space. And again. All right, so this would be an improper node. Again, all of these trajectories are approaching my node, which is at the origin 0, 0. And this one is improper because all trajectories except for this one along the x-axis are tangent to that straight line along the x-axis. So proper versus improper. We call a node a sink if the trajectories approach the critical point, and they're called sources if they recede from it. So both of these up here would be considered sinks because the trajectories are approaching the critical point. So I like to think of rivers, and if you have a source of a river, the water is flowing from that source and then away from it. A sink would be, for example, like a delta. So at the bottom of the Mississippi River Delta, that would be a sink where all of the sediment and water is rushing toward that area. So sink versus source. So we actually now have two different classifications for nodes. They can be proper and improper. And on top of those classifications, they can either be a sink or a source. Another type of critical point is called a saddle point. We've seen saddles back in Calc 3, and these are very similar. So a critical point is a saddle if the trajectories approach along one axis and then recede along another. So let's see what this is going to look like. We just need one set of axes here. And again, I'm just going to make my critical point at the origin. We want to approach our critical point along one set of axes. We want to recede from it along the other. Whoops, other direction. And fill in the quadrants according to these lines. So if we're close to the x-axis, we're moving toward, but then as we get toward the y, we're moving away. Make sure you indicate an arrow to say which direction that solution curve is going. And so we can do this similar effect in all four quadrants. And so on and so forth. And so I'll highlight that node here. All right, so here's an example of a typical saddle point. If we look back above at our phase portrait that we found using Wolfram Alpha, we see that one of our points was a saddle point. So let me scroll back up to that. So this point right here was a saddle point. So you'll notice that we are approaching the point along this line, but then we get this saddle-like behavior here, which means we must be diverging away from it here. All right, so there's our saddle point. All right. So then for all critical points, we can classify them as stable or unstable. Stable means that the solution curves nearby a critical point remain close. So that's the important phrase there. Nearby solution curves stay nearby. and then they're unstable if they're not stable. In other words, the solution curves continue to recede far away from your critical point. And so we have this remark right over here, based on the above definition, all sinks are stable, whereas all saddle points and sources are unstable. All right, so I think it's fairly clear why sinks are stable and sources are unstable. Sinks are emanating toward your critical points and sources are receding away from it. So that fits right in with the stable and unstable definition. Saddle points are kind of odd because at first they start heading toward your critical point, but then they take a curve and they move away and then they continue in that path for eternity. So they do get close for a moment, but remember, we're looking at what happens as t goes to infinity here for stability purposes. We can also classify equilibrium solutions as stable or unstable, and that's just by looking at the associated critical point and looking at the stability of that point. So that stability classification carries on to the equilibrium solution. All right, we have yet another classification for critical points, which is called a stable center. I just want to emphasize here that centers are always stable. And so what it is it's a critical point surrounded by simple closed trajectories. So let's plot a coordinate system here first. And keeping with my main setup, let's go ahead and let our critical point be at the origin. And all we want to do is surround this with closed trajectories. These might look like circles. These might look like ellipses. We just want that they're simple closed trajectories. So I'll draw some ellipses. I'll make them elongated in the X, and then just pick some kind of orientation. But whatever orientation you have for the first trajectory, they all should follow. So I'll put a few more trajectories here. All right. And so highlight my critical point. And so this one, these trajectories are not emanating directly toward our critical point. However, if you look back up at our definition of stable, is again that nearby solution curves remain close. These solution curves, or these simple closed trajectories in the stable case, never get too far away from our solution point, which is why we consider this stable. So this is a stable center. So just as saddles are always unstable, centers are always stable. All right, there are two different types of stability. There's stable, which we have just defined, but there's also what's called asymptotically stable. So a critical point is asymptotically stable if it is stable. So first you have to have stability, and that every trajectory that begins sufficiently close to the point also approaches that point. So if you begin sufficiently close, then you're going to approach. So that's the second classification, or the second condition to be considered asymptotically stable. So based on the above condition, stable nodes are asymptotically stable, and the center pictured on the previous page is stable but not asymptotically stable, right? So we fail condition 2 in the case of the center, because even though some of those trajectories begin close, they never emanate all the way into that critical point. They stay a certain distance away. All right, for our final classification for critical points, we're going to talk about different types of spirals. So we say an asymptotically stable critical point around which the trajectories spiral as they approach the stable point is called a stable spiral point, also known as a spiral sink. So let's go ahead and plot that. I'm going to need 3 different plots in this white space. So make sure you leave room for 3, not just 2. So a stable spiral is what we'll draw here on the left. So here's our coordinate plane. We'll keep with our node in the middle. And what we want to do is we want to spiral into this node. So maybe I'll make mine look a little bit of an elliptical spiral. And since we want this to be stable, we need our arrows to be pointing towards the critical point. All right, so here is an example of a stable spiral. Again, I made my spiral look elliptical, but your spiral might look more circular. We have an unstable critical point around which the trajectories spiral as they emanate and recede from it is an unstable spiral point or a spiral source. So this is going to look very similar to this picture that we just drew. It's set for, instead of emanating toward the critical point, we're emanating away. So this is going to be an unstable spiral. And we'll keep our critical point in the middle. This one I'll draw a little bit more circular. And now we want to be moving away from our critical point, so we're spiraling outward. All right, so two different types of spiral. And this last guy here we're going to talk about is a closed trajectory. So it's possible for a trajectory to spiral into a closed trajectory and essentially get stuck. So let's take a look at what that's going to look like. We'll sneak in here a closed trajectory. So I will let my critical point be at the origin yet again, and I'll highlight that here. And then go ahead and draw whatever your closed trajectory is going to look like around that critical point. I'm going to draw mine to be circular, and then pick some kind of orientation. And then what I want are other solution curves that are spiraling in towards, but then getting stuck into this closed trajectory. So maybe we'll have some of these. And so for this, I like to think of astronomical orbits. So for example, some asteroids that are getting stuck in an asteroid belt, and then they just keep moving along this trajectory around a planet or whatever it may be, and they're just stuck in that trajectory. So this would be a closed trajectory. These would be stable, but not asymptotically stable. So I'll just write stable, but not asymptotically stable, because they get stuck in that trajectory and can never get any closer than where that is. All right, so let's do an example. We want to find each equilibrium solution of the given system and then use a computer algebra system to construct the phase portrait. And then from that phase portrait, classify the critical point as a center, saddle, or a spiral point. So what I want to notice here is I want to take a look at this differential equation. And this is a second order differential equation in X. And when we defined finding critical points, we looked at setting a system of first order DEs, each piece equal to 0, and solving simultaneously. So what I want to do is I want to transform this second order DE into an equivalent first order system. So this is a skill that we practiced back in section 4.1. So I'm going to notice that this is second order. That means I need to define x1 and y1. So let's let x1 equal x. Let's let, or excuse me, not x1 and y1, but x1 and x2. Let's let x2 be the first derivative, which is x1 prime. And then the second derivative will then just be x2 prime, and that's going to equal negative 2x prime minus x minus 4x cubed, which is minus 2x2 minus x1 minus 4x1 cubed. Now you'll notice what they ended up doing is they let x prime be y. So in other words, they let all of the x2s be y, and then they let x just essentially be itself. So if we do that, our system becomes y equals x prime, and actually let me just write that in the opposite order. X prime equals y, so we're just pulling this, darn it, from here, and then we're going to say x double prime, whoops, is just a y prime, so y prime equals a negative 2y minus x minus 4x cubed. All right, and so you'll notice that's precisely what they got for this system right up here. But I just wanted to go through and derive that so that we're all on the same page. And then looking at this system, if we set these both equal to 0, we get right away that, of course, y equals 0. So let me drop out my y term. If I factor out a negative x, I get 1 minus 4x squared equals 0. So I get x equals 0 and x equals plus or minus 1/2. So I'm getting, whoops, sorry, made a mistake here. Let's make this a plus. And since we're plotting in the real coordinate system, we will not count any imaginary values for our critical points. So we just get a single critical point here, 0, 0. And then it says, use a computer algebra system to construct a phase portrait and classify the critical point. So what I'm going to do is I'm going to draw my axes right down here. I will plot my critical point. And then let's switch screens back to Wolfram Alpha. And all I'm going to do is I'm just going to change my input right here. So my new DE was x prime equals y, and y prime equals a negative 2y minus x minus 4x cubed. And I'm just going to keep with the same restrictions on x and y, namely plus and minus 5. And I just hit return here. All right, and so you can see what's happening here. It looks like a very elongated elliptical spiral, and you can see these solution curves emanating towards our critical point. So what I'm going to do is I'm just going to essentially copy this picture over onto my notes here. So let me go back to my notes. And we had this very sharp spiral emanating into our critical point, and then where it got wider, we could kind of just see almost starting to look like straight lines. All right, and so then for the classification, this is a stable spiral and it's also a sink. Actually, we'll just leave it as a stable spiral. We'll save the sink for notes. All right, so here's our critical point. Here is our classification. All right, so we're going to complete these notes with a final example here on the next page. First, we want to solve the system by inspection. That means don't do elimination, don't use the method of eigenvalues, but just think about what this solution would look like. And then finally determine whether this critical point 0, 0 is stable, asymptotically stable, or unstable. and you use a computer algebra system to plot the phase portrait and classify that critical point as a center saddle node or spiral point. All right, so when you're talking about solving a system by inspection, we're literally just going to take a look at this DE and ask ourselves, what is a function where when I take its derivative, I get itself back out times 2? So what function, when I take its derivative, gives itself back out, but then just doubles? And so you should be thinking of, in general, what's a function when I take its derivative, I get itself back out, first of all. And that function that we see all the time is the exponential function. But we don't just want e to the t. We need to double it, so we need an e to the 2t up top. So for x prime equals 2x, our solution by inspection is going to be x of t equals e to the 2t. But remember, we could have any kind of constant out front. So I'm just going to call this the initial position x naught here. And then the second DE is very similar. We want a function whose first derivative is itself times -2. So of course, we just need to sneak a negative into that exponent. All right, so again, this is just by inspection. Oops. By inspection, we have those solutions. All right. So now that we have our solutions, we would like to plot this using a computer algebra system. And so let's switch back here. And what I'm going to do, since I can't do it with a general constant in front, I'm just going to choose that constant to be 1, and it'll give us an idea of what's happening. So we want e to the 2t and e to the -2t and x and y. Let's see if this will plot with the t's in there. Not sure. Nope. Okay. So instead, what we'll do, yeah, the fact that I have x's and y's and then t's, I think is confusing it. So instead, actually, let's go ahead and just do this one by hand. This one's easy enough to figure out since we have simple enough functions. So if we take a look at this, we have the following. All right, let's look at our x of t function, and let's look at what happens as t goes to infinity. So as t goes to infinity, the limit of the x of t function is also tending towards infinity, right? So this exponential function keeps growing and growing. And what about the y of t function? Right, that one is tending to 0. So this exponential function dies out since it's e to the -2t. So we have along the x-axis, we're going out to infinity, and along the y-axis, we're approaching our critical point 0. This is going to give us saddle-like behavior. And by the way, I didn't mention this, but if you set each of these functions equal to 0, I think we can all agree that we only have one critical point here at 0, 0. So understanding this limiting behavior of x of t and y of t, we can now sketch it. Here is our critical point. And we said that the x of t function is tending out to infinity, whereas the y of t function is coming into 0. And then you can fill in everything accordingly. And we can now see our saddle. Recall that saddles are always considered unstable. So This is an unstable saddle. And you might also notice, okay, this is additional, but we also have that if you multiply x of t and y of t together, we had x naught e to the 2t times y naught e to the negative 2t. These two guys, their exponents add, so we get x naught y naught. So if I just call that some other constant k, what I have is x times y equals k, or y equals k over x, which look like reciprocal functions for various k values. And that's exactly what we saw up here in this saddle. So this is just kind of another way to visualize these solution curves. So this concludes our section 6.1. Again, we were talking about stability and the phase plane. And we will continue on in chapter 6 with section 6.2 next.